In this lesson, we're looking at the law of sines, which we picking up from last time, but looking at something called the ambiguous case, SSA, side-side angle. All right, what is the ambiguous case? The ambiguous case occurs when one uses law of sines to determine missing measures of a triangle when given two sides and an angle opposite to one of those sides. Back in geometry, that was called SSA, side-side angle. In this ambiguous case, three possible situations can occur. So one of the cases, no triangle can actually exist with the given information, or we can end up with one possible triangle, or two distinct triangles may be formed that satisfy the given conditions. This is why it's called the ambiguous case, because there's several different things that could be interpreted. So let's look at the different possibilities. All right, given side A and side B, and angle A of triangle A, B, and C, which means you were given two sides and an angle, which is our SSA. These are the six possible scenarios. The first four deal with the angle being acute. The last two deal with the angles being obtuse. So, if we had an acute angle, and there's our side B, we have to determine the height. Once we have the height, and we compare it to the opposite side A, we notice that A is less than the height. And if that's the case, you can see no triangle can actually be formed. While the second situation says we got angle A, there's our side B, and our height. But if the opposite side A is actually equal to the height, as you can see, we actually do create one particular triangle. So you can begin to see, based upon the measurements given, the possibilities that can occur. Next situation, we've got angle A is acute. There's our height again. Now this time we're going to compare the opposite and the adjacent. If side A opposite is actually larger than side B, you can see that there is one particular triangle that is formed. Next, there's our acute angle. We've got our height. Now we begin to look at A. If A is actually shorter than B, that's what we're focusing on. A is smaller than B, but when I compare it to the height, it's actually longer than the height. And it creates two possible triangles. So this is a very unique situation. Next, we'll go to obtuse angles. There's our angle A and side B. Here we'll first look at if A is actually shorter than B. As you can see, no way can a triangle be formed. Let's also consider if A was actually equal to B. If it was equal to B, same situation, no possible triangle. Last one, got our obtuse angle. There's side B, and if now A was longer than B, we can see that there is a possibility of a triangle. Now, this is a lot to consider, so let's put it in a flowchart form. So to determine the number of triangles, in this situation, we were given one angle and two sides. The angle was either going to be acute or obtuse. If the angle was acute and you were given two sides, we can compare the two sides. Either the opposite was greater than or equal to, or the opposite was less than the adjacent. If the opposite was greater than or equal to, that's where we saw there was exactly one triangle. When the opposite was less than the adjacent, we had to first find the height. And we found the height from last unit. Height was simply the adjacent times the sine of the angle. Well, we would either have two situations. The opposite was either going to be greater than the height, or the opposite was less than the height. If the opposite was greater than the height, we had two triangles. If it was less than the height, there were no triangles. So when we transition to obtuse angles, again, you were given one angle and two sides, the opposite and adjacent. Well, the opposite could either be greater than the adjacent or less than or equal to the adjacent. If it was greater, we had exactly one triangle. If it was the other situation, no triangles. So we'll use this as a resource when determining numbers of triangles. Let's actually do a problem to show how this works. Here we're given angle A, 28 degrees, side A is 7, and side B is 11. So let's first determine where angle B is. Now, because we have the opposite is less than the adjacent, according to here, if the opposite is less than the adjacent, we must first find the height. So let's go ahead and do that. The height is right there. I'm working it out the long way. Sine is opposite over hypotenuse, h over 11. Multiply 11 on both sides. There's the 11 sine 28, which was the adjacent times the sine of the angle. So we saw before, the adjacent times the sine of the angle. That gives us a height of 5.16-ish. So that means A is greater than H. The opposite is greater than the height, which means the triangle will exist. When we look a little closer, the height is less than the opposite, which is also less than the adjacent. Very unique situation. In that case, this was one of the ambiguous cases that gave us two possible triangles. So let's go ahead and find the first triangle, meaning let's find angle B using the law of sines. Sine A over A, sine B over B. Substituting the values in, solve for sine by first multiplying by 11 on both sides. To get B by itself, we'll use inverse sine on both sides. So this is what goes into the calculator. I'll leave that clear. All right, so I'm just going to put this one just to demonstrate. So inverse sine, there's our fraction, 11 sine 28 all over 7. We get about 47 degrees, so 47.5. 47.5, the measure of angle B, so B, 47.5. So what we found are the measures of that first triangle, but the ambiguous case told us that there's actually two possible situations. So let's look at the second. So this is where we left off. Now we saw from earlier, we need to consider if this side 7 here was over here. We now have our second possible triangle. Well, this angle here is the exact same as this angle here, 47.5. We have us an isosceles triangle. That's how I know these two angles are congruent. Well, this angle here is supplementary to that 47.5. So we can find it by simply subtracting it from 180 degrees. That gives us our 132.5, which means this second angle here, 132.5. If I consider these two angles here, the 47.5 degrees, we can consider it angle B from the first triangle. So we'll call it B sub 1. Whereas the 132.5 is the angle B from the second. So we'll call it B sub 2. Well, we'll use these two angles to help us find this third angle here. Because it's part of the triangle, all three angles add up together to get 180. So these two angles added together should actually be less than 180. We get the 160.5, which is less than 180. So in fact, that second triangle does exist. So let's go find that third angle. That 160.5, which was these two, take that from 180, that gives us the 19.5, which is the measure of this angle. So now we can begin to see the two separate triangles. And in these two triangles, it does still keep the original given measures, meaning the angle A, 28 degrees, they both have it. Measure of side B, they both have the 11, and they both have side A, which is 7 units. We'll do another one. Measure of angle A, 40 degrees. A is 9, B is 13. So there's our triangle. I'll go ahead and label angle B. Well, let's confirm, because A is the opposite and there's the adjacent. The opposite is less than the adjacent. According to the schematic, opposite is less than the adjacent. We must find the height. So let's go find the height. As our height, formula simply said, take your adjacent, multiply by the sine of the angle. So therefore, height is about a little over 8. And 8 is less than, and the 9 is greater than that 8. So, because the opposite is greater than the height, the triangle will exist. And when we look closer, again, that unique situation. The height is less than the opposite, which is also less than the adjacent. That's the ambiguous case where we have two possible triangles. So let's go find angle B from the first one, or B sub 1. Using our law of sines, substituting our values in, multiply 13 on both sides to get B by itself. Now it's time to do the inverse sign to get B by itself. So this is what we'll go into the calculator, and that gives us a little over 68 degrees. So we know angle B, 68.2. So let's work on the second triangle. We've got side A is 9, but if this 9 was over here, we've got our second triangle. Well, the 68.2 here is the exact same as 68.2 there. Again, another isosceles triangle. The measure of this angle is the supplement to that 68.2. So we find it by simply subtracting from 180. That gives us 111.8. And so we'll use these two angles to find this third angle here. Again, these two angles here have to add up to be something less than 180. Because it is, we know for certain this second triangle does exist. So, to find that third angle, we'll subtract that 151.8 from 180. That gives us 28.2. So, we can see the two separate triangles. They both have the 40 degrees, the 13 for B, and the 9 for A. So let's look at the review of the steps. If we were given side A, side B, and angle A of triangle A, B, and C, and, well, that's SSA, two sides and an angle. And we know that the height is equal to, we'll call H being the height. So first thing we did, we determined if the triangle existed. We saw from our little chart, no triangles exist in two separate places. No triangles here, no triangles here. So that was an acute angle, opposite was less than the height. And of course, we found the height by using that formula. And if it was obtuse, obtuse was less, the opposite was less than or equal to the adjacent. Once we determine if triangles exist, we'll consider how many. There was either, so we use the flow chart to determine how many. If there was one triangle, we just use the law of sines to determine the other missing values. If there were two triangles, again, we would use the law of sines to determine that first angle B. Once we got that angle B, the first one, we can find the second angle B. It was simply the supplement of angle B sub 1. That's essentially what we did. And we're able to find all the C's by subtracting the A's and the B's from 180. Because these three angles, A, B, and C, have to add up to be 180.